I am pleased to introduce Evan Passaris from Atkins. Evan is currently a consultant in Atkins Ground Engineering and Tunneling Department in Edinburgh, following his full-time employment for 15 years as a technical director with Atkins. He is a chartered engineer with more than 45 years of international and UK experience in engineering consultancy, in geomechanics and underground storage caverns. Evan's past professional involvement in the UK and abroad as a leading consultant in geomechanical engineering over a period of many years has contributed in establishing him as an expert in the geomechanical design of underground geostorage schemes. He is recognized across the industry for leading and delivering geomechanical solutions in several underground gas storage projects in salt caverns in the UK. He is the author of numerous technical papers on underground storage and maintains strong links with academic researchers as visiting professor in the School of Earth and Environment of the University of Leeds. Evan has been involved since the 80s in the design of the Teesside hydrogen storage salt cavern, originally developed and operated by ICI. So it's our great pleasure to have you, Evan, with us. I'll just bring your presentation in a moment.
Thank you. Thank you very much.
How can I go full screen? I need help for full screen. Yeah, now I found the key. Sorry. So it should be fine now. Evan, please.
Lovely. Thank you. Right. Very briefly, there's an outline of what is to come. You can read it later. Let's go straight into the actual presentation because we're running out of time. I was told very clearly by Hadi. So the concept of underground geological storage of hydrogen is obviously there because we need it. My predecessor here in the presentation explained why we need it, so I'm not going to say anything more about this. I would like to go straight and talk about what kind of investigations we normally need to implement in order to look at the caverns. We always start with drilling, of course. And the drilling nowadays is done by directional drilling. You have a platform from where you actually pad. You can drill several holes, which eventually are going to be the holes which will lead you to the cavern. The important thing is when you're using directional drilling to make sure that there are certain limits. The maximum inclination has to be kept below 35 degrees if you want to have an absolute control of the actual installation later of the completion. And another point, as you are approaching with the drill hole in the location where the cavern is going to develop, have to leave at least 100 meters above the cavern, where it have to be vertical. The hole has to be vertical for absolute control of the operations later. Maximum inclination should be 1 degree there. Once you drill the hole, a number of tests, down the hole tests, need to be implemented in order to get the details of the properties of the geological formations that lead from the top to the very bottom. And once you're finished with the classic geophysical logging program, there's another set of tests that you can do. They're optional. Down the hole ground penetration radar is one of the techniques which you normally employ in order to find any abnormalities that may exist in the area where we'd go and develop the caverns. And of course, we need to use the hydraulic packer formation test, which will allow you to determine the in situ permeability of the salt and also to define what is the threshold pressure, or if you like, the frac pressure of the salt in particular. Once you developed the drill hole and you finished with your test down the hole, every core which has been collected needs to be taken to the laboratory. There's some physical tests, there's some mineralogical tests, the tests which are used for the design of the solution mining techniques that are going to follow, but equally important, we need to do some mechanical tests to find the characteristics of the salt in particular and some of the other geological materials. We need to know the quasi-static properties of the salt. By quasi-static properties, I mean, for example, the Young's modulus, the Poisson's ratio, tensile strength, uniaxial compressive strength, and of course, the shear characteristics, shear strength. But equally important, you need to know the creep characteristics of salt. Salt is a unique material that creeps continuously when it's loaded, and we need to define the characteristic parameters which are used in the modeling of the time-dependent behavior of salt by using special techniques. Having gathered all this information, which is the results from the drill of the holes, the in situ tests inside the wells, the laboratory tests, and of course, all the information that we have from the seismic surveys in the area, we can build a holistic model of the geological area we're going to develop the caverns so that we can decide where is the best optimum location, if you like, for developing our caverns. The history of the salt caverns is an old one. 2,000 years ago, the Chinese started by extracting salt with the bamboo, if you like, techniques, bamboo sticks, and originally they were interested in the salt, of course, but they ended up by producing an empty space. And years later, when the rest of the country started using the same technique of solution mining, they thought, wait a minute, we create a big space. Can we use it to store inside something? And they started storing originally oil, hydrocarbons, natural gas, and of course, since the mid-60s, mid-70s, I would say, we started using hydrogen. Hydrogen was stored for the first time in the UK, and it's there to be used, the technique, and nothing new about it. Already we have 3 large caverns in the United States in Salt Dome. At the moment, they're operated by ConocoPhillips, they're operated by Praxair, and of course by Air Liquide. They're not used for producing energy. It's stored that's used specifically for various processes that are required by the companies. And in the UK, we had since the early times when ICI used to run the show in the United Kingdom for the salt caverns. We had 3 caverns. We still have them there. They're operating nicely in Teesside. They're small caverns. They're no more than 75,500 meters, cubic meters capacity. They're at a relatively shallow depth, I might say, so no more than 360 meters. And they are peculiar shapes, as you can see. They're like flat pancakes. The reason why they're still like this is because the thickness of the salt is relatively small. And if you want to maximize the volume, you have to have them large diameter and flat. They're also quite unique in the sense that the roof of the caverns is very, very close to the overburden, which is a problem. Because as you'll see later, I will tell you, you have to keep at least 90 meters from the overburden. And for this reason, we can't use these caverns as dry storage. They have to be wet storage. In other words, we're using the brine as the means of injecting brine inside and expelling the hydrogen, or if you want to later inject the hydrogen, the brine has to be thrown out. Of course, they're not throwing out the brine. They have large ponds of saturated brine that they use for that purpose. So that's the case of salt caverns in the UK. When you are in business of developing caverns to be stored, to be used as a storage facility, we employ the technique of solution mining. It's a straightforward technique. What you do is you drill a hole, you lower 3 tubes. The first tube is used for injecting water. You don't need to use fresh water, you can use seawater. Seawater is not fully saturated, therefore capable of dissolving salt. Once you've dissolved the salt, you produce brine. The brine then comes out on the surface with the second tube that you have. And then you allow some of the insolubles which are in with the brine to be settled down before you send to the pump house. And from the pump house, you either dispose it back to the sea in an environmental friendly way, or if you're lucky enough to have nearby an industry that uses the brine, they're using it to produce sodium and chlorine from it, no problem. The third tube is used to lower in the cavern during the development the so-called blanket. It's an inert material. We're using usually nitrogen or sometimes compressed air. In the past, we used to use oil. And that is to actually lower or rise the interface of the brine and the blanket to allow you to control the shape of the cavern. You can actually control the shape of the cavern nowadays relatively well, and you can produce practically any shape you like within limits. So once the brine cavern has been created, you have to get rid of the brine. You inject the hydrogen inside, and the hydrogen, as it is injected into the brine cavern, is forcing the brine to go out through the so-called debrining string. Now that debrining string, which continuously throws out the brine, essentially, if you keep on doing it continuously, you'll block it, because salt salt normally deposits on the inside part of the tube. So every now and then, fresh water is injected inside the debrining string to control the fluorescence process. One important thing that you need to have in a salt cavern, which is used for storage of hydrogen, is to have the SSV, the so-called subsurface safety valve. This is installed not too deep, not far from the surface, to make sure that if something wrong happens in the surface, you don't lose control and you have a blowout. So the SSV is an important part of the overall system that we have for storing the hydrogen inside the caverns. Once you've finished with the SSV, then you have to start removing the so-called debrining string. Remember, the cavern is already in very high pressure with the hydrogen. You can't just pull them out like this. You need a special rig that you have there, which is called the snubbing rig, and one by one, slowly and carefully, you remove the parts which form the string. And essentially, after that, you're ready to start operating your cavern without any problems. But you need on the surface a very special part of the equipment, which is the so-called the wellhead. We can't use anymore the wellheads that we used to employ in the past for natural gas. We nowadays have to use special wellheads designed specifically for use for hydrogen storage. A number of firms are already in the business of producing that. A number of these wellheads already being tested and used at the moment in various projects. And the trick is to make sure that these caverns they should be equipped with pure metallic sealing ball valves, and in the standard form, they should also have a double seal against the well pressure. And it's a straightforward, if you like, technology to have these new wells used. When we come now to consider how we design this cavern specifically for the use of hydrogen, there are some geometrical things that we have to take into consideration to start with. We look at the actual cavern layout, and that's going to reflect the fact that you are going to be using a certain specific stratigraphy. The quality of salt is coming into the questions that we need to be answered, and of course the depth of the salt formation. But one of the most important things is the actual thickness which is available. If you're working to develop, or you plan to develop caverns in domes, diapiric salt, no problem, massive. The thickness is there to be used, but if you're working about layered salts, you should aim to have thicknesses of the order of 200 meters approximately. So in this example that I'm showing you, for this 200 meters thickness of salt, which is a typical thing, the first thing you have to remember is you need to leave a gap between the roof of the cavern and the interface between the salt and the overburden. And that safety pillar should be larger than 60 meters. Equally important is the little chimney that you leave. The chimney is that part of the cavern which is below the LCCS. LCCS stands for Last Cemented Casing Shoe. Okay? Between the LCCS and the top of the cavern, you have to leave approximately something more than 30 meters. After that, you have to consider, of course, the actual diameter of the caverns. The diameter of the caverns is typically of the order between 80 meters, 90 meters sometimes. And for that kind of diameter of caverns, the spacing between the two caverns, in other words, the thickness of the pillar that separates the cavern, and it's quite important, this thickness, because you need to have no structural interaction between adjacent caverns. You can have one cavern at the minimum pressure, the other cavern at the maximum pressure, and there should be no interaction. So the thickness of that pillar should be of the order of 220 meters, which essentially means for this kind of diameters, an axis-to-axis distance of approximately 300 meters. At the very bottom of the cavern, you should still leave a small thickness of salt of the order of 10 meters, slightly more than 10 meters, to ensure that there'll be no structural interaction between the sump. Sump is the lower part of the cavern, where all the insolubles are deposited, and of course the underlying geological formation. So all in all, these are the typical geometrical issues that you have to consider. But you also have to consider that salt is not an ideal material. Sometimes you have some shear zones, some big faults, etc. You have to keep a distance between these unwanted geological features and the walls of the cavern. And typically nowadays, for hydrogen storage caverns, we'll be using the same technology as the one that we have for natural gas, which is something like more than 3 times the maximum diameter. And the same kind of limit should be the one that we're using if we're dealing with a domal salt, the end of the stalk, if you like. So they are the typical, if you like, characteristics that we have for the caverns. But that's geometry. Let's look now at the operation of the caverns. 3 things are important in the operation of the caverns: your maximum pressure, your minimum pressure, and equally important, how fast you're allowed to extract or inject hydrogen inside a cavern. Not so much the injection of the cavern, but how fast you can extract it. So if we look at the maximum pressure, when the pressure is high in the cavern, small microfractures are bound to open in the walls of the cavern, which means that the permeability of the salt is going to increase, and hydrogen will be allowed to start moving outside of the cavern. However, if that maximum pressure is kept at a reasonable level, then that zone of, if you like, disturbance, if you like, of the zone of the salt permeability is going to be relatively limited. In my experience, it's not going to be more than a meter and a half. And more importantly, every time you are lowering the pressure, all the hydrogen that has gone inside the salt is going to come back into the lower part of the pressure inside the cavern. So, provided that you're going to keep the maximum pressure below 80 to 85% of the geostatic stress at the depth of the LCCS, that's the important thing to remember, not in the cavern, at the depth of the LCCS, then you're okay. And that will ensure that the fracture creation of the cavern will be avoided if you maintain, therefore, this pressure in the absolute less than the least compressive stress that you have in the walls of the cavern. There's another thing you have to remember. You may be, if you have too high pressure, allow the hydrogen to start permeating behind the LCCS and through the interfaces that you have either between the cement and the salt, the cement and the steel. And to make sure that this is not going to happen, you have to ensure that the confinement that you have at the depth of the LCCS is high enough. And there's an equation that we've been using for years in the case of natural gas, which is to divide the maximum pressure by 0.85 and make sure that this is lower than the confining pressure that you have from the horizontal direction. So that is used for hydrogen storage cavern, and as well at the moment, maybe we have to increase a bit the safety factor when we come to hydrogen because it's more mobile. Minimum pressure is normally designed so that you can have control of the creep and therefore the substance on the surface, and also make sure that the integrity of the cavern is left untouched. We make sure that we normally have the creep, the minimum pressure higher than 25 or 30% of the geostatic pressure. Another criterion that we should be using is to make sure that if the minimum pressure is such which allows the roof of the cavern to move, that movement should not permit the LCCS area to have a strain of more than 1%, in other words, 10 millimeters per meter. If that is permitted, then you're going to have problems with the integrity of the caverns as perhaps the result of shear modulus. Maximum flow, at the moment you heard earlier, figures saying about 10 bars a day. Believe me, nowadays we're using 20 bars a day without any problems. We have been successfully using 20 bars a day for natural gas. And now that I'm talking to you, we started about 2 weeks ago further work to define whether it's possible to go to 30 bars a day. And my feeling is, yes, we will be able to do that. Whether that will be okay for hydrogen, something to be seen and develop practical experience. But at the moment, my belief is that easily for hydrogen we'll be able to have between 10 and 20 bars without any problems. And to complete the design of the caverns, we have to realize that we need to have some geomechanical model of the rock caverns, of the salt caverns. And this is obviously taking into consideration all the properties that are developed from the material. And we need to make sure that we have a coupled thermomechanical analysis of the response of the caverns. If we look now at what we do for testing and monitoring, we start always, before we develop the cavern, by testing the actual casing. You pressurize the casing before you develop the cavern. You make pressure of the order of 1.4 megapascals on the surface, but make sure that this pressure is not exceeding 90% of the geostatic stress at depth, or indeed doesn't exceed 8% of the burst pressure of the cavern. Once the cavern is developed, you have to make sure that it's tight and holds the nitrogen, the hydrogen at depth. So we have to do a mechanical integrity test in which what we do is we inject the hydrogen on the top, just below the casing shoe, and we monitor whether the interface between the brine and the hydrogen is moving upwards with time. It lasts 96 hours approximately. You need a probe that will actually monitor the interface between the hydrogen and the brine, and you determine the calculated leak rate, the CLR. And this has to be less than the maximum detectable leak rate, which at the moment, majority of the technical statutory authorities are defining as being 50 liters a day. What happens if it is more than 50 liters a day? Well, provided that it's less than 150 liters a day, you don't reject the well. You still need to do some further investigations, and if they're okay, then you end up by using it. But if it is more than 150 liters a day, then you have to reject this. We have recently what, the last perhaps 5 or 6 years, a new gadget in the market which is ideal because instead of using a probe to monitor the surface, we're using sonar techniques. It's a gadget called Summit by Socon, and it's a tremendous improvement because it allows to increase the accuracy that we monitor the interface, and we have better opportunities to do the MIT test. What are the differences between the two materials? Right. Unfortunately, the compressibility factor of hydrogen, as you can see, there is more than one, which means that essentially for the same kind of storage conditions, the hydrogen is not as effective as the natural gas. If you look at the Joule-Thomson effect, that's good news because it's negative, which means that we don't have any problems during the thermodynamic operations of the cavern. And essentially, it means that we don't have the need to take care of problems for condensates or hydrates. And if you look at the density and the viscosity of the hydrogen, then you'll find out that because of the dynamic viscosity of the hydrogen and combination together with the density, the difference of pressure between the wellhead and the cavern is practically non-existent, which makes life much easier. And if you look at the overall performance of the two caverns, the two types, modeling that has been done has shown that there's very little difference between the two materials, and therefore we can easily control hydrogen caverns in the same way we have been controlling the natural carbons. Decommissioning, straightforward. I'm not going to dwell on it. You can see the results, the details later. All I can tell you is we start all at the subsurface. Once we remove the hydrogen from inside, then we hand over the responsibility to the surface guys. The surface guys salvage whatever they can and throw the rest of it away. And when you come to the abandonment, the technique is plug it, seal it, but make sure that before you actually plug and seal it, that there's an equilibrium between the brine or the water that you put inside the cavern and the temperature which exists there. You have to leave some time in order to come to a relatively good equilibrium. Sometimes you can spend some more money if you want to heat up the brine of the cavern that you put in the cavern to ensure that you speed up the process. It's a matter of deciding what to do. And there are 3 different techniques which are used in order to produce the cavern, to produce good plugs, and please spend some time, look at them later. This is the result of work has been done by SMRI. SMRI is the Solution Mining Research Institute that leads all the work which is done internationally in the solution mine caverns for storage purposes. Thank you for your time.
Thank you very much for this extremely informative talk. We have room for one quick question, and please do keep your questions for the discussion panel also, because that's the moment we can get more in depth. Any questions? We have a few already, maybe on. Very brief until we get the next speaker.
Okay. Geological from Geostock. You didn't mention anything about the cyclicity use of the caverns. Do you have any opinions on that?
Well, at this very moment, Geostock is leading the work on cyclicity. This is perhaps why you're asking the question. No, it's all right. I can answer it. First of all, let me tell you, I've been working with Geostock for many years. We started a close cooperation when we started storing LPG in Humberside, and I work with many of your colleagues, etc. For a period through my life, I ended up working for Geostock for good. So, good work that you're doing on cyclicity. It is a problem. The problem is not acute, if I may say so, because we have found out that the effect of, if you like, the fatigue of the salt itself is not as acute as we had expected, especially for the rate of the cycling we have, because it's a relatively slow rate compared with fast cycling rates. But everybody in the business is waiting with anticipation to see the good results you're going to produce. So if you want more details about cyclicity, I'm listening to you.
Thanks, the best answer. So let's thank Evan. He's going to be here with us for the whole period of the summer school, and we will get into the depth of these discussions in the discussion panel. Thanks very much.
For your time.
Thank you very much.